Have you wondered why handles on doors are as far as possible from hinges? When you want to open a closed door, you push it from the opposite side to the hinges, and the door revolves around these hinges. If you try to push it, let's say from the center of the door, you will need to apply a larger force to obtain the same rotational motion. Also, you usually push as perpendicularly as possible with respect to the plane of the door. If you push with another angle, you will need to apply a larger force to obtain the same rotational motion. For example, if you push towards the hinges, the door will not revolve. Of course, for the same conditions of angle and distance, the larger the force applied, the larger the effect on rotation of the door, so the larger the angular acceleration. All we are doing is changing the rotational motion of the door. If it is closed initially, we want it to revolve around the hinges. This is everyday experience, but there is very interesting physics behind this. Consider all this. Let's define a new physical magnitude to describe the ability to change the rotational motion. We define the torque of a force applied to a solid object as tau is equals to the cross product of r vector times the force. The torque is the cross product of the position vector r and the force F. The origin of the position vector is always at the axis of rotation, the hinges in this case of the door. This vector goes from the rotation axis to the point where the force is applied. This is a cross product, a product between vectors that considers only those components that are perpendicular to each other. This means that if both vectors are parallel, the cross product is zero, and if both vectors are perpendicular, the cross product is maximum. The result is another vector which points in a direction perpendicular to the previous two. The torque is perpendicular to the plane that contains the position vector and the force. This definition contains all the points I mentioned before. If the force is applied parallel to the position vector, which in the example of the door would be parallel to the plane of the door, the torque is zero. And we have no change in the rotational motion of the door. If we apply the force closer to the rotation axis, the torque is smaller, which is why we need to apply a larger force to obtain the same effect. The units of torques are newtons per meter. We will consider the torque to be positive if it points up, which would mean that the change in rotational motion is counterclockwise. If the torque points down, it will be considered negative and the change in rotational motion is clockwise. Another way to write the equation of the torque, avoiding to write explicitly the cross product, is by writing only the component of the cross product that contributes, which would be by multiplying the magnitudes of both vectors and then multiplying them by the sine of the angle between them. In this case, we need to be careful with the sign of the torque, thinking on the direction of the effect of the torque on the rotational motion of the object. If there are several forces acting on an object, the net torque will be the sum of the individual torques. Let's think of an example. Let's consider the following. At this object, there's a force acting at a distance r and of a magnitude f, and it's pointing upwards. Then there's a second force acting at a distance to r from the axis of rotation, and the magnitude is 2f, but it's pointing downwards. And there's the third force acting also at a distance of 2r and magnitude 2f, but acting with a certain angle. The total torque is going to be the sum of the three individual torques, and for the first case I will only look at the magnitudes and consider the angles, of course. And the first contribution will be just r times f, because the angle between r and f is just 90 degrees and the sine of 90 degrees is 1. The contribution of the second force is going to be 2r multiplied by 2f, but that's going to be negative because it's going pointing downwards, so it would induce a clockwise change in the rotational motion. And the third force is acting to the right and upwards, so only the upwards component of this 2f force is going to make an impact. So the total torque will be 2r, because it's the distance, multiplied by 2f, which is the magnitude of the force, but then multiplied by the sine of 45 degrees. And that will be the total net force of this system of three forces acting on this object.